This is your senior first starter speaking, and today we are going to be talking about the air conditioning, pressurisation and ventilation systems on the Airbus A320. First thing to note is that this chapter is really split into three parts. The first being the air conditioning part, second being pressurisation, and the third being the ventilation. We'll start with the air conditioning, and with that, this is the system that provides air at a nice temperature and a good pressure into the cockpit and the cabin. These zones are, there's three of them. There's the cockpit, the forward cabin and the aft cabin that we can control, and they're all controlled independently. The air normally comes from the pneumatic system, but it can also come from ram air or indeed a external low pressure air connection. So the temperature is all controlled fully automatic, although we do have some input via the overhead panel and can monitor it on the status display on the eCam. So what is this system made up from? If you look at the architecture diagram of the system, you can see that normally the air comes via two packs. It enters via the pack control valves, then goes through the packs and into a mixer unit. At this point, we could also provide air using emergency ram air or using an external low pressure ground connector. Post the mixer unit, where the air is mixed with air from the cabin already, via the heap of filters and the cabin fans, it then goes through to the relevant zones. At this point, the air can be topped up with hot air that is taken from upstream of the packs via the hot air pressure regulation valve, and then each individual zone has a trim air valve associated with it. All of this system is controlled automatically via the ACSCs, which is the air conditioning system controllers. So let's talk about the packs. First of all, know that the pack has air supplied via the pack flow valve. This air tends to be somewhat higher temperature and pressure than what we would like to give the passengers, so we need to bring both of those values down a fair whack. The way we do this is using an air cycle machine and heat exchangers. So the air enters into the pack, goes through a primary heat exchanger, which initially cools it. It then goes into a compressor, which compresses the air, making it actually hotter and higher pressure. It's then put through the main heat exchanger, and because the air is hotter and higher pressure, it actually loses energy far quicker. And then comes through a turbine, which reduces the pressure on the air, reduces the temperature of the air, and then supplies this air to the mixer unit. Also worthy of note is the aircraft is capable of opening valves that is able to bypass different sections of the pack if it needs to. And the air used in the heat exchangers is taken from outside the air pack using a ram air inlet, which is not the same as the emergency ram air. This is a different inlet. After this, we'll talk about the valve that controls the packs. You've got the pack control valve. These are pneumatically operated, so they're moved via the air pressure, but they are electrically controlled. That signal comes via an electrical signal. And what it does is it regulates the air pressure going into the packs, and obviously shuts it off if it needs to. With regards to this, there's a spring that will close the valve if there's no air pressure upstream. And the packs also close automatically in the event of a pack overheat, but only on the ground. When the engine's being started, if we push the engine fire push button, the ditching push button, or the pack push button. So, next we've got the mixer unit. The mixer unit mixes cold, fresh air from the packs with the cabin air. This comes from the cabin recirculation fans. And really, it's a bit like a bus bar in the electrical unit. It's a meeting point for the air before it goes into the cabin. So, what about the other inputs? Well, you could also have emergency ram air. This ventilates the cockpit and cabin and is mainly used to remove smoke in the event that we have a fire in the cabin. It also can be used to ventilate the cabin in the event that both the packs have failed. When you push the ram air push button, the emergency ram air will open in the event that you haven't pushed the ditching push button, of course. When the ram air push button is pressed, the outflow valve will also open 50%. This provides a through flow, so if you can imagine, it's like opening two ends of a Pringles can, and the air is just going to flow through it. But the outflow valve is only going to open provided that your delta P, so that you haven't actually pressurized the cabin. So you're going to have to get it down, depressurize the cabin, and then push the ram air push button to get maximum smoke clearing effect. This is achieved via the checklists. So we've also got a hot air pressure regulating valve. This is used to help control the temperature by bleeding in a little bit of hot air to the really cold air coming out of the packs. This, like the pack valve, is kept closed with a spring, and it's also electrically controlled or pneumatically operated, exactly the same. We tap hot air and then we warm up the air before it goes in the cabin, and it will close if you push the hot air push button. If both lanes on one of the ACSCs fail, so if in the event that you have one of the ACSCs fail, one of the computers that control this system, if you have a duct overheat, because we don't want to be putting hot air down a duct that has a leak, or in the event that some of the trim, either the cockpit trim air valve or if both the cabin trim air valves fail, at this point the hot air will shut. Really, this doesn't have that big of an effect. Been in a few aircraft where this has happened and this has failed, and honestly, it just makes the temperature go up and down a little bit more, but it's perfectly manageable. The trim air valves are what will supply this hot air, and each one of them is controlled by the relevant ACSC. The ACSC1 controlling the cockpit and ACSC2 controlling the ones in the cabin. So, let's talk about the ACSCs that we've been talking about so much. These are the controllers that control the air conditioning system, funnily enough. The air conditioning system controllers. They're both automatic. We have sensors that will monitor the temperatures, and they're located in the cockpit, in each of the lavatory extractions circuits, and also in the galley ventilation. They use this to then supply air at a relevant temperature for the demand being asked. In the cockpit, we can select temperatures from 18 degrees centigrade all the way up to 30 degrees centigrade overhead. And the cabin crew can use the FAP, best named thing on the Airbus, to plus or minus 2.5 degrees either side the value that we set in the cockpit. So, what do these ACSCs do? They will modulate the temperature by changing the bypass valves within the pack, as well as the pack flow valve and the ram air inlet that provides the cooling air into the packs. They will, however, shut this ram air inlet that provides that cooling air during takeoff and landing, this being mentioned as from takeoff as soon as you set the power to the gear being uncompressed, and during landing it's the moment the gear is compressed to 20 seconds after you've reached 70 knots. But effectively, what do you need to know here? You need to know that that ram air thing should be shut on takeoff and landing. Either way, at my operation we generally take off without the packs on anyway, so it won't have that much an effect, and it only really has the effect after landing. So we can select pack flow using a rotary switch in the cockpit as well, from low to high. However, the system will always be in high in the event that we're only using one pack, if we're using the APU bleed, and also in terms of if we were to select low, the system would still deliver normal flow if you can't reach the temperature that you've asked for. Normal is normally limited to 90% flow on the ground with both the engines running. If the bleed pressure is too low to meet the cooling demand, the ACSCs, these controllers, will actually increase the minimum idle on both the engines to raise the bleed pressure to provide that air. So what this means is if you're having problem maintaining cabin temperature, you're going to see that in the power of your engines, probably during a taxi, and so you're going to get more powerful engines if you're having trouble maintaining cabin temperature. So it's just something worthy to think about. And also, it will do this if you're using an APU, but this time it just increases the speed of the APU, and you won't notice that, obviously, in the taxi. Lastly, why don't we talk about the cockpit footwell heaters? There is an option to fit them. However, I can't really be too much of an expert on these because, sadly, my airline keeps my tippy toes cold and hasn't bought them. But despite the fact my feet are the temperature of 2 nicely chilled pina coladas, this is all the information I can give you. They're controlled on the overhead panel with switches. That's about it. So, what happens if there is a failure in the system? It's quite a robust system, really, although they do fail. So first of all, you've got 2 ACSCs, and in the event that you lose both of the lanes, they have 2 lanes each. So each computer has 2 lanes, to, a backup within itself. So in the event that one fails, it will automatically switch. It'll give you a maintenance message and nothing more. In the event that both the lanes fail, you're going to lose the pack that ACSC controls, and you're also going to lose the hot air valve with the trim air valves. So if you lose an ACSC, then effectively you'll be now flying around with one pack, and it's going to be relatively hard to control the temperature. That's the effect. You can have other fails. So what happens if, say, the compressor or turbine seizes in the pack? Well, funnily enough, that doesn't stop it. Your pack's still going to work using just the heat exchangers, and the valves will open with the relevant conditions to supply the air to the heat exchangers. However, it's going to be low flow. You're not going to get as much effort out of it, and they're going to be working harder to provide the relevant temperature, so you're going to have problems, but it will still work. Next, the hot air valve can fail, but as we've said before, basically it just means it's a bit harder to control the temperature. It's still perfectly doable though. And lastly, if the trim air valve fails, again, it's the same as the hot air valve failing, really. You just find it harder to control the temperature. Funnily enough, if the hot air valve fails open, there is no effect, so it can fail and there be no effect whatsoever. Other than a system maintenance message. Okay, so why don't we talk about how we are going to control and understand what's going on in this system. So, with the air conditioning system, funnily enough, there's no air conditioning panel on the overhead panel. On this, there are a number of switches and knobs. Knobs. But the main switches we use are really the 3 knobs that control the temperatures. You can select a temperature between 18 and 30 degrees. We also have a hot air push button, which will have a fault light that comes on if there's any overheat. We've also got the pack push button switches, which we use quite a lot. And there's a pack flow selector, which we use in the event that there's low passenger numbers. We'll select low. In an Airbus A319 or A320, you're looking at about 130 or less, or an Airbus A321, you're looking at 160 or less. However, in these troubled pandemic corona times, we normally have it on high to enable maximum ventilation in the cabin. Ram air is also up here, and as previously mentioned, this will open the ram air inlet, and in the event that we are pressurized, it's not going to do anything else, and in the event that we are depressurized, it will open the outflow valve 50% and allow this through flow of air and removing all of the nasty smoke that we want to get out of the cabin. Then, looking on the ventilation panel, we've got the cabin fans push button, and we use this to stop recirculation of cabin air into the mixer unit. So, looking onto the status pages, we've got an ECAM bleed page that we can access, and on this it will tell us the pack outlet temperatures, valve positions, and all this sort of stuff. Of course, normally you're looking for an amber or a green flashing indication that something is gone awry, but the key numbers here is you're really looking for air not more than 90 degrees centigrade to enter the cabin, because we don't want to cook our passengers, and you're looking for the pack compressor outlet to be no more than 260 degrees centigrade. They will go amber if it goes above this. So 260 degrees centigrade, I mean, my lord, that is hot. That is hot. Yeah. So we've also got the ECAM condition page. So here it shows you the orientation of the trim air valves and the hot air valve, and the temperatures in each section of the cabin, as well as the temperature of the air that we're supplying to that relevant section. Next, we come to the pressurization phase of this chapter. So, this system has 4 general functions. On the ground, we keep the outflow valve open to enable the doors and such to be operated properly. Then, while we're before takeoff, we go through a pre-pressurization phase to pressurize the cabin to avoid large changes in pressure during the climb. Next, pressurization. In flight, computers will adjust the cabin altitude to make it as comfortable for the passengers as possible. And then after landing, we go through a depressurization phase where we slowly release the residual pressure and go back to let the ground function take over so we can operate the doors and such. This system consists of 2 computers known as cabin pressure controllers, CPCs, that control it. There's also potentially, if you go to your Airbus dealership, there's an optional extra of a residual pressure control unit that helps depressurize the aircraft after we land. There's an outflow valve, which is the main hardware of the system, a control panel to control it, and 2 safety valves. Normally, the 2 computers, the 2 CPCs, control the valve, and they do this each with their own associated motor, but there then is a third motor that the manual control uses that can then operate the valve. Any one of these motors can control the valve. There's 3 modes you can do this entire system with: automatic, semi-automatic, or manual. Automatic, the FMGS runs the show with how high the desired airport is going to be. Semi-automatic, you set it on the overhead panel using a rotary knob, and the manual switch is using a toggle switch to literally move the valve to where you want it to go. So, main components. Let's talk about the computers. So first of all, there's 2 of them. They're digital, and they receive signals from a variety of sources: LGCIU, ADIRS, the FMGC's throttle lever angle from the EIU, and even the emergency ram air valve position. So when one CPC is active, the other one stays on standby and can take over if it needs to. They're both linked up and generate signals for the ECAM. In the event that you change to manual mode, each CPC, even if it's failed, actually has a backup section that has a separate power source, and these can still monitor the pressure for the ECAM and allow you to control some sense of control anyway. The outflow valve itself is on the right hand side of the fuselage after the aft cargo door, and it's below the flotation line. Again, it's powered by 3 motors as previously decided. Safety valves, we have 2. They will activate if you go above 8.6 psi or below 1 psi ambient, and this just makes sure that the cabin doesn't pop like a party balloon. They're located on the rear of the pressure bulkhead, sort of in the tail, and they are above the flotation line. If we have a residual pressure control unit, as we said, this deals with depressurizing the aircraft on the ground, though the CPCs can do this as well. In terms of operating the system, the CPCs will swap over every flight, 70 seconds after landing, or if the one fails. Key figures is that we limit the cabin pressure to 8,000 feet generally, although we can obviously land on airports up to 14,000 feet above mean sea level, whenever the hell you want to be doing that. We get the landing elevation and the QNH all out of the FMGC unless we're using the knob, and if we use the knob, it uses the captain's barrow reference to use that sort of calculation. In terms of pressurization modes, we've already sort of talked about it, but we've got a ground mode. It does limit pressure changes from 500 feet per minute, but basically it has the outflow valve fully open to just make sure that we can use the doors really. In terms of takeoff, we have it will pressurize the cabin at a rate of 400 feet per minute until 0.1 psi. And we then go into the climb phase, and during the climb, cruise and descent phase, what do we care about mainly is that the rate of descent doesn't go too much. We're talking about maintaining like 0.1 psi pressure in the cabin, and we don't want any sort of climbs or descents more than 750 meters per minute really, and also we don't want to go above 8,000 feet. In the event of an aborted landing, the cabin pressure through the pre-pressurization phase will be set back to delta P plus maybe 0.1 psi, which is not that much. So, in terms of manual pressure control, we do that using the toggle switch, as mentioned. You do this with blips. It takes 5 or 7 seconds for this blip to take effect. You just press it, see what happens. You are going to have to set your outflow valve to fully open after landing to depressurize the aircraft. And you know it's fully open when the valve turns amber on the ECAM. In terms of ditching, we have a push button we can press. This closes the outflow valve, emergency ram air valves, avionics ventilation valves, pack flow valves, and forward cargo isolation valves. Basically, it turns the plane into a lovely boat in the event that you want to go for a swim. How do we control the system? We have a panel on the overhead panel, and it includes the flicky switch, a mode selector push button, the landing elevation knob, and the ditching push button. A lot of these things we've sort of mentioned already about how they operate. One thing that is worth noting, however, is if you switch to manual for 10 seconds and then put it back to auto, the CPC will switch from one to the other, which is an option if you're fault checking, I suppose. Last, we have the ventilation system. The ventilation system ensures ventilation of the avionics bay, the batteries, as well as the lavatories and the galleys. First of all, talking about the avionics ventilation, it's a fairly complicated system, but essentially it involves 2 fans to move air through the equipment in the avionics bay. It gets this air sometimes from outside of the aircraft, and sometimes, well, almost all of the time, through the gaps in the panels in the cockpit, drawing the air out of the cockpit. The main components of it are the fans that do this, as well as valves on the outside of the aircraft, the skin air inlet and outlet valves. There's also a skin exchange heat exchanger which cools the air, which is kept inside of the aircraft, and there are valves that bypass it. There's also an air conditioning inlet valve that allows air conditioning to supply air to the system if we need to, as well as isolating the skin heat exchanger if we want to. Last of all, there's an avionics equipment vent controller. This is the computer that controls this entire system. Now, there are several configurations that this system can be in. It depends where we are, whether we're on the ground or in flight. Essentially, what you need to know is that the computer will control it to make sure the avionics equipment is adequately ventilated. System is closed circuit whilst in flight, and it can be closed on the ground so long as everything's within the relevant operating temperatures, and it can also be open circuit on the ground if we need to cool things down a bit. Furthermore, there's an intermediate configuration we can use whilst in flight, again, if we need to cool things down a little bit. There are 2 more configurations to talk about, the abnormal as well as the smoke configuration. Abnormal configuration essentially is just when you select the blower or the extract push button to override, and it draws air from the air conditioning to then cycle through the skin heat exchanger to make sure everything feels good and the right temperature. And then we've also got the smoke configuration. This very simply vents the air overboard whilst we're in flight. You do this by selecting both of the inlet and the outlet switches to override. This chucks all the smoke out of the aircraft. So if the controller fails, it opens the exchanger to the system in smoke, and it also the inlet will remain in the position that it had before the failure, and the extract fan just keeps on chugging. So this is the safest configuration it could be, and it'll chuck any smoke overboard whilst keeping things cool. Battery ventilation, it's a lot simpler. We have a Venturi. It sucks air in from outside the aircraft around the batteries. It sucks air from inside the aircraft around the batteries, keeping them cool, and then it will vent it overboard using a NACA duct. And then we finally got the galley and lavatory ventilation. So this basically just makes sure that the air in the galley and the lavatories, you don't want that pooey air getting into the mixer unit. It's not healthy. So what we do is we extract the air from the lavatories and the galleys, there's some fire and smoke detectors that are in their system at that point, but then basically it takes it all the way to just about near the outflow valve and then vents it overboard with a fan, so that makes it sure it doesn't go back into the cabin. So how do we control this system? So we have a panel, funnily enough, a ventilation panel, and basically there are two switches we care about, which is the blower and the extract. Again, you know, if there's a fault light, which can be due to a problem, then it will alert you. And also, if we want to go into smoke config, just remember you've got to push both of them. That will start venting everything overboard. We also have the pressure page. It just shows you the position of the valves. We have the inlet and the outlet valves. They appear in amber if there's a fault with them, and also you get amber X's if the sensors can't tell you what position they're at. Obviously this is important with regards to pressurizing the aircraft and those sorts of things. So, you eager beavers, thank you very much for joining me on this chapter. In the next chapter, we'll be discussing the hydraulic system of the Airbus A320. But in the meantime, have a lovely, lovely, lovely day.